Someone tells you to do something, you just do it, right? Life lesson, no, you gotta think about it. Weigh the costs with the benefits. This isn't personal finance class, but that's an important concept. Some people say I should skip it because it's kind of a complicated idea. However, even though it's not super basic as far as the math that it covers, guys, it's super practical. It's super practical. If you guys ever take a biology class or a chemistry class, or really much of any science class in high school or in college, exponential growth and decay is a really important idea in those. Because there are things called radioactive elements.
They're radioactive?
Yeah. That decay. But they decay in ways that they have things called half-lives. And their half-lives meaning however much you have today, how long it takes for it to decay away. Because you guys know what decay means, right? The body decays. Even the Bible says we return to dust. From dust we came, and we'll return to dust. Bodies decay. It just takes a while, right? Some people say like, oh, it's biodegradable, no big deal, so I'll throw my apple core out the window. What are they talking about? It's not really litter because it's going to decay. Composting, it's a huge thing these days because you're trying to, work with the environment and trying to work with making everything sustainable and all this jazz. If you talk about biodegradable material, some like snazzy restaurants you go in, they're going to have like these paper bowl things instead of plastic because paper, in a sense, biodegrades. It degrades away, it decays away. It doesn't leave as much litter. Whereas plastic is kind of like it's just there forever. Let's not even go talking about the turtles. But anyway, coming back. So growth and decay. Decay is a big deal with composting, with bodies, with radioactive elements. Some radioactive elements take thousands of years even to get to half of what they were. Bodies would be just totally dust by then unless it was preserved in some really crazy way, like the mummies in Egypt. But otherwise, bodies go away really fast as far as compared to thousands of years. Maybe just a couple hundred years, it's gone. But radioactive elements can take thousands of years to actually decay away. There's this thing called carbon-14 dating. It's a big thing in the science community. Is evolution a thing, or is creation a thing, or maybe both? Carbon-14 is talking about an element that was present and then it takes so many years to decay. And so you can say, hey, I think it's decayed this much, so how many years have passed? Decay. Growth. Have you guys ever realized that when someone on a school campus gets sick, pretty soon it spreads?
Yes.
No. Why? Because things grow. Bacteria grow. Viruses get passed, right? If you ever have talked to a scientist who's in a lab, they have these like petri dishes and they're trying to grow, right? They're trying to grow different, whatever. It depends on what they're doing. Stopping. But growth, there's exponential growth in nature and there's exponential decay in nature. So even though the math is a little bit complicated, it's super practical and something that you might totally see again one day. Or if nothing else, you might hear it in like a sermon or in someone giving a speech or a motivational speaker or a teacher talking about, exponential growth. Everything is getting so bad. It's because the swoop goes up so quickly. Or exponential decay. Maybe everything is falling apart so quickly. It's because it's swooping down so quickly. These are words that are used a lot. So these equations you guys were writing down in your notes, I know they look complicated mathematically speaking, but they're super practical. So let me get away from the complicated for a second. You guys ready?
Yes.
Let me get away from the complicated for a second. We'll come back. What if I was just to ask you something like, hey, which of these are bigger than 1? You ready? Which of these are bigger than 1? Kind of like our whole circle on the quiz thing. Circle the ones that are bigger than 1. And what if I just threw out random numbers? Like, let me do it in black. How about like 1.05? How about like 85%? How about like 0.01? How about 120%? How about 1.13? And how about 0.99? Who's greater than 1? Someone give me one. Raise a hand. Who sees one that's greater than 1? Jared.
1.05.
Is it greater than 1? You guys agree?
Yes.
Me too. Totally higher than 1. Awesome. What else? Daniel.
1.13.
1.13 or 1 in 13 hundredths, right? 1 in 5 hundredths. Good. What else? What else do we have? Only the guys are volunteering? Yeah. Okay, what do we got? 120% is more than 1?
Yes.
Completely. What else is greater than 1? 85?
Nothing.
No. Okay, hold on. Yeah. That's where it starts to get tricky. Because 85% is huge. It's so much bigger than 1. It's 85 until you remember it's really a decimal. Because any percentage is a decimal if you actually think about the quantity of it. So if you were to move the decimal, how are we supposed to move it? Twice. Isn't it really 0.85? Which is like 85 cents. It's less than $1. We can think about this as $1 if that helps. 85 cents? Nope, it's lower. So why did this one win? Well, because if you move it twice, it means the decimal places, where do you end up? Got it. So is this one bigger? No. Is that one bigger? No. Is that one bigger? Yeah. Guess what? Ready? We're going to attach this to growth and decay. If these were talking about rates, of change, this is a really snazzy, actually even calculus deals with rates of change. If these were rates of change, guess what? This would be growth. Whereas this one would be decay. So what's another growth one?
120%.
This would be growth. And I heard this one too, right?
Yeah.
Any overall rate that's bigger than 1, right? Isaiah is going to be growth. Whereas anything that's lower than 1 is going to be decay. Now hold on. Those equations a second ago were super complicated. But can we just take this idea? Can we go back to those equations and see if they make some more sense?
Sure.
Because this makes sense, right? Higher than 1, lower than 1. Higher than 1, growth, growth, growth. Lower than 1, decay, decay, decay. So, what do these equations actually mean? Do you guys see 1 plus and 1 minus in these equations?
Yeah.
Do you see them? There's a 1 plus and there's a 1 minus. What does the 1 plus and the 1 minus say? This equation is going to show growth if the base, which remember, here's the exponent. The base is anything that's underneath the exponent. Not the number that's multiplied out in front, that's a coefficient. But the base is what's underneath. If the base is greater than 1, it's growing. The base is greater than 1, it's growing. So what am I going to put down here when I talk about decay? It's not 1 plus, or it's not going over 1. It's going, what do you see in the math?
Under.
It's going under 1. Yeah, look at that minus, right? So for growth, you're going over 1. And for decay, you're going under 1. Now, when I started writing out that homework on the board, you guys were like, oh, man, she's done it now. Just skip it. Forget it. It's going to be too hard. Because look at all those numbers. And there are commas and there are dashes. But what if I told you that's kind of all there is to homework? Now, not exactly, but close. Figuring out when there's growth and figuring out when there's decay by figuring out is the base bigger than 1, which means I'm going to be swooping up and growing, or is the base less than 1 and I'm swooping down and decaying? But remember how I said that there's some practical application to this? Since there's some practical application, the problems might start to look a little weird. So let's go forward just a little bit more. And let me ask you guys some questions. Okay? Homework is going to start by, in many ways, them asking us, them asking me, them asking you, to identify what's here in the mathematical equation. Okay? What's in the mathematical equation? Now, do you remember what I was just a second ago? If this is looking too complicated, think about what we just did. Bigger than 1, lower than 1, right? we talking about? That's what's in our phones right now. Bigger than 1 or lower than 1?
Bigger.
Bigger and
Smaller.
lower. So can't I right now, just right now, can't I call this one a growth equation? Is that cool?
Yes.
Let's just start there. And then this one's going to be what kind? Decay. Your parents are like, hey, what are you learning today in math? It's super awesome. Oh, exponential growth and decay. No big deal. Sounds super snazzy, but it's not that complicated. The exponents can get hard. We've been dealing with exponents all chapter. But growth versus decay. Now, hold on. That's not all that they're asking. They're asking for find the initial amount and the rate as a percent. Then evaluate. Okay, in my mind, when directions start to get long, I start to get confused. So I'm going to go ahead and do 1 is find A. 2 is find R. Remember, I'm lazy, so I like to break it down. Then, okay, what am I doing? Okay, cool. Then cool. And then what's number 3? Basically, plug in 5, right? So for each of these, I have 3 things to do. What is A? What is R? Plug in 5. Now, you guys wrote down those little equations a second ago. Do you see an A in both of them? Both of them have A's. Okay. So, number 1 for both of these problems says, pull out the A.
5.
Yeah. A is the coefficient that's outside of that whole power expression. So yeah, it's just 5. And if they give me a word problem, I can even like label it 5 grams or 5 pounds or 5 ounces. But they didn't tell me what is growing. They just gave me math, so 5. But what's A in this one, guys?
0.2. Or 2.
No, you're right. You're right. 2 tenths. 0.2. You're right. Okay, so initial amount. That had 5 to begin with. This had 0.2 to begin with. We're reading kind of in this equation a story. There's 5 of something, and it's growing. But how fast is it growing? That's what number 2 is asking. How fast is it growing? Now, this gets a little complicated, but not if you remember above 1, below 1. Because R, if I go back to the equation from a second ago, R just answers how much above 1 or how much below 1. That's all R answers. So if I come back to that equation and if I say, okay, hold on, mathematically speaking, I know, who likes to talk about math? I mean, I must because I teach it, but coming back. Do you see R is how much more than 1? The math shows it. R is how much more than 1, and R is how much less than 1. So let's check out the math equations that we're looking at and say, okay, all we have to do for R is say how much more or how much less. Now, careful. They do give us something really specific. How do they want this to end as a percent? But we can start with a decimal if it's easier. So check out the first equation. We have 1 point, oh dear, it doesn't like one. We have 1.07. So if you guys just answer my question, how much more than 1 is 1.07? Oh, careful, not 0.7, but 0.07. Yeah, we just have to get the whole thing in there. If I was to take away 1, what is left? 0.07. So it's growing, but wait, we can't stop there, right? How would we write that as a percent? Because that's what they want. We would have to go ahead and, right, move that 2 places to the right, and we would have 7, or 0.7, but the 0 doesn't have any meaning. 7%, because it's just a little bit above 1, right, guys? Okay. It's not like 1.20, which would be 120%. It's just 1 and 0.07. Just 7% more. So far, we figured out who A is, the initial amount. We figured out what the rate is. Well, wait, hold on. Can you do not just above, but also below? Think about it in money. If you have this in your pocket with a little dollar sign, how much more than $1 do you have? How much change do you have? 7 cents. Yeah, 7%. Think about money. If you have this in your pocket, how close are you to $1? 2 cents. That's what my R is. My R is the 0.02 or 2. It's as easy as money. How much more than 1? How much less than 1? We're so stinking close to being done. What's the very final step? Yeah, so now in context, every equation is telling a story. You have 5 to start with. This thing starts growing by 7%. And if it's growing by 7%, it's kind of like 7% per day, per week, per year. Some things grow really fast, some things grow really slow. Kind of depends. We'd have to have the word problem to know what to label the time with. But the long story short is, okay, so where is it at after 5? Where is it at after 5? You guys heard me say that exponential growth is like a real life thing. Sometimes it's good for stuff to grow. Sometimes it's bad for stuff to grow. You're like, no, slow down. So if someone's trying to predict it, like, it's growing, we gotta slow it down. Like whether it's a disease, whether it's bacteria, whether it's whatever it is, if you're trying to slow it down, you want to know, if I let this go 5 days, what's gonna happen? If I let this go 5 hours, what's gonna happen? If I let this go 5 years, what's gonna happen? Sometimes it's good, but sometimes it's bad. So this is saying, hey, what's going on after 5? Well, to know that, we gotta plug it in. Hey, we took a quiz where you guys should have done a lot of plugging in, right? You had to plug in for the evaluate problem, but just once. You had to plug in for the table a few times. Hopefully you got your scoop. There it is. But coming back, we just need to plug in one value. That's it. So y equals. Now, guys, do you see how this 1.07 is kind of messy? Now, find the t. This 5 needs to go in his spot. Kiddos, we still have 2 or 3 minutes. Come on, calm down. Calm down. But check it. Is this something that any of us are going to be able to do mental math? No. Exponential growth and decay are real life problems with messy quantities. This is totally a calculator thing, so feel free to have your calculator. Some of you have figured out how to use the exponent button on the calculator, and some of you haven't. But if worse comes to worse and you can't figure out how to use the exponent button, or you have your phone, couldn't you do it the old-fashioned way? If worse comes to worse. And don't you realize that this parenthesis means times? And you're going to have 1.07 how many times? Okay, it's going to be annoying, but are you going to be right?
Yeah.
Yeah. It's going to be annoying, but you're going to be right. So I do want you to keep going on this one. These are ones that will need a calculator on this final step. But has it been super hard up until the plug into your calculator part? I hope not. Just thinking above or below. So for number 3, we're going to do the exact same thing using the equation up above, just instead of plugging in 5 to the growth equation, we're going to be plugging in 5 to the decay equation, but we're still going to be using our calculator. Now if you can use or figure out how to use that exponent button, your life gets a lot easier. You can just say, hey to the 5th power, or hey to the 5th power. Because we have to, for each of these, the direction said to plug in. Yeah. Oh, because it's 5 times, and this tells me how many. Does that make sense? Now, guys, there's one type of problem we didn't get to talk about, so I'm going to pull it up really quickly on the webcam or the document camera. I want you guys to see over here, what are those weird 13, 14, and 27, 28 problems? Do you guys see how they give you words in 13 and 14? And they're going to give you words in 27 and 28. Now, hold on. If this says increase by, is that growth or is that decay? Increase by.
Oh,
Growth. And we have an equation that we can plug into as far as how much it increases by. So check it. You can read the words and compare it to your equation. And guys, when it says increase by 65%, do you realize that's how much it's going to go up? So I put it in the R spot. And then, when it tells me of 10,000, isn't it telling me how much to start with? Guess what? All they're telling you is take the math and put it into an equation. I just did a homework problem for you. If you're smart, you can figure way out the door. Bye, guys. Yeah, homework is on the board, and I just did number 13. Beta 8's the calculator quiz. You guys feeling it?
Yeah.
No.
Make sure you have a calculator. Make sure your group has a calculator. Make sure it has batteries.